Good morning, ladies and gentlemen. My name is Olaf Kievit from TNO, and I would like to introduce you to the Mating 4 project. I was planning to be in Munich today to talk to you in person, but unfortunately the increasing measures related to COVID-19 make that impossible, so therefore I'm presenting this from my home office. This is the content of my talk. First of all, I'll be taking you through some of the project essentials, talking to you about the objectives. Then I'll be going into details on the automotive and semiconductor domains, which are both subject of Made in 4. Then I'll be talking about data, machine learning, and how they relate. Then I'll be showing you some of the highlights produced in the first 2 years of the project. And finally, I'll be giving you an overview of the presentations given by Made in 4 partners during SEMICON Europa this week. So starting with the Made in 4 project essentials, the consortium is quite big with some 47 partners in 10 different countries. And we've been on this project for over 2 years now, targeting to end October next year. We did get a 6 months extension. And the size of the project in terms of project months is also quite large, 10,000 project months, and over 100 million euros in size is the budget. This slide shows the partners in Made in 4. We have companies active in metrology, robotics, and computing components. We have OEMs in metrology equipment and EDA companies. We have several manufacturers of devices and also in the automotive sector. And we have RTOs, standardization institutes, and academia to support all that. The objective of Made in 4 is to develop new productivity boosters. And the first of these boosters has to do with metrology and inspection tools who can increase the productivity both in semiconductor and automotive industry. And the second booster is related to cyber physical systems, making those ready for Industry 4, involving higher data rates and smarter acquisition and processing, and also the use of data to improve productivity and predictability. As mentioned earlier, the project covers both the semiconductor and automotive domain. And what we are trying to achieve in both of these domains is to get from the more conservative reactive manufacturing, which uses primarily feedback loops, to more predictive manufacturing that goes also into looking forward and using iterative design and manufacturing loops. If you look at the automotive and semiconductor domains, you'll find that they are actually quite comparable. The number of wafers produced per month, for example, is well over 10 billion, and it's quite comparable to the number of cars that's produced every month worldwide. Both of the domains produce highly sophisticated products with many different features or configurations. Both have a high level of automation, but there are also differences. The semiconductor manufacturing process typically is quite stable, trying to change in years typically, whereas the manufacturing process in automotive industry is continuously changing and improving. So these domains, they share similarities in design and manufacturing flows, although of course the content of these design and manufacturing modules differs. But because of this analogy, we can share innovation in machine learning-based methodologies, and that enables the transformation, as mentioned earlier, from the reactive to the productive domain. Yeah, data is the new oil, is what people say. It's clear that there's more and more data being collected, pushed to the cloud. Sensors are added everywhere. You see that more and more data is also collected and stored for future usage. And there's also increasing use of all sorts of algorithms and machine learning to process all these data. But data alone is not sufficient. You have to add context in order to make use of this data. So adding data analytics and artificial intelligence helps create information. That is data placed in a context, and that is what you need if you really want to make use of this data. Cyber physical systems play a role in this because, well, the interaction of the physical world, the computing world, and also embedded intelligence, this is what really creates information and what turns data into meaningful data, being information. And in that aspect, it's also important to mention artificial intelligence. A lot of similar terms used there. Artificial intelligence we see as the container term. Machine learning is part of that, where you're looking at the behavior of a system. If we use neural networks there, we use brain-inspired systems to do this machine learning. And if we go even deeper into deep learning, that's a particular implementation of neural networks. But in fact, these are all different specific types of artificial intelligence. Digital twinning is also a term that you hear a lot and also quite important for Mating 4. On one hand, you have the traditional modeling where you were using physical models that require little data, but you put in the physics to understand the process. On the other extreme, you have machine learning where you don't put in that much physical knowledge, but you're using a lot of data to understand what's going on. Combine the two and you get a possibility to get a virtual representation of a system, of a process, and that's what we call digital twinning. This brings me to the project highlights, and the first highlights that I want to present to you is from IMEC. IMEC is an important partner in the project, and one of their tasks is to supply samples to the partners. In this case, they created samples of back-end of line devices, and with those devices, programmed overlay is possible, and partners can use these samples to test their metrology tools. And compare the results to other data available. Another very interesting result is produced by Excelum, and actually Simona from Excelum will be presenting this in more detail later this morning. Last year, Excelum produced a first prototype of a new X-ray source. Which has a higher power and in this way enables a higher throughput for X-ray metrology tools. Another example of a project result was produced by Mentor and Global Foundries. They have combined data measured on a wafer. And by combining this data, it was shown that you can get a better prediction of your process parameters. Shown in the bottom of this slide is on the left-hand side the situation before this data was combined, showing quite a significant spread in process parameters. And once you combine this information, the spread is very much reduced, leading to a much better prediction of the process. A next example of a project result concerns the simulation of a laser annealing process, in this case targeted at back junction formation. A project result produced by CNR, STMicroelectronics and UPB. This simulation was validated using TEM and XRD data. And if you look at the comparison slides, you see a very good fit of the data to the model, showing that the simulation are quite good and can be used also to model this process. Another example, this time from the automotive domain, FCA, Tower, and TU Delft optimized, in this case, the imaging of spot welding defects. And this can help in car manufacturing to classify these defects better and improve the quality control and analysis of these defects. And the final example that I wanted to share with you today is a metrology target produced by PTB. And in this case, it's a target with a very intricate geometry produced to calibrate scanning probe microscopes. And there's also the detailed photo on the right-hand side shows it's not a simple geometry. There's a very specific angle targeted there in manufacturing, and PTB was very successful at doing this, and the prototype is currently being evaluated at the project partner Near Field Instruments. Then finally I want to show you what other presentations from the Made in 4 project will be shown during SEMICON Europa. Later today, you'll be hearing presentations by Simona Laza from Excelum, as mentioned earlier, on the MetalJet, the technology for X-ray generation. Juliette van der Meer from Broeker will talk about other advances in X-ray metrology made by Broeker and Made in 4. And the last talk in this session will be by Thomas Ashby from IMEC, and he'll be talking about the privacy-preserving amalgamated machine learning algorithm, so the PAML, and what's been achieved in the Made in 4 project on that topic. Tomorrow there will be a presentation by Ovadia Ilgayev from NOVA in the SmartX session. And that will be on innovations in integrated metrology at 10 o'clock. And later this week, on Friday, there will be another session involving Made in 4 presentation starting at 10 o'clock. And that will be on artificial intelligence and robotics. There will be presentations there from Jean-Hervé Tortaille, LTM, looking at error detection using ellipsometry and how to use that to do metrology. Giulio Vivo from CRF will have a presentation on digital twinning and specifically applied on energy modeling and management of the body and assembly shop floors in automotive industry. Merav Sejev from Billionator and Alfio Minisale from Kamau will have a joint presentation on robotics and specifically also the social aspects of robotics. Very interesting topic. And the last presentation will be by Lior Viagelli from Applied Materials on defect inspection, and then specifically the computing challenges associated with that. So that was the last slide of my presentation. Thank you very much for your attention, and I hope that you will enjoy the other presentations of the Made in 4 project in the Made in 4 in the SEMICON Europa conference. Thank you very much.
Good morning, good day, dear visitors. My name is Juliette van der Meer and I work for the company Brooker as manager of collaboration projects. I'd like to thank the organizers to give me the opportunity to show the advances we have made in X-ray metrology in the Made in 4 project. This is the overview of my talk. First, I'll give you a short introduction on the company Brooker and the X-ray metrology solutions we offer. I'll touch on the scope and the goals we set ourselves for Made in 4. And then I'll show you a couple of examples of XRF and TXRF applications in the semiconductor industry, followed by a presentation of the key results we have obtained so far in Made in 4. I'll wrap it up with an outlook of what's coming next. There will be a few minutes time for questions at the end of my talk. If you now listen to the recorded version, please send your questions to the organizer or contact me directly. My email address is on the title slide. Brooker is a key supplier of measurement instrumentation that serves academia and a wide range of industries, including the semiconductor industry. The Brooker organization is split in 3 groups. Brooker Biospin provides NMR and EPR equipment. Brooker Kievit does mass spectrometry, optical spectrometry, and CBRNE detection. My business unit, that is the Semiconductor X-ray, is part of the Semiconductor division, and we sit in the Brooker Nano Group. The Brooker Semiconductor X-ray business unit provides a wide range of X-ray-based metrology and inspection solutions for the semiconductor process, for the front end, the middle, and to the back end of line. We offer micro X-ray fluorescence for metal film analysis, TXRF, total reflection XRF, for metal contamination control, X-ray diffraction for crystalline phase analysis and epitaxial film characterization. X-ray diffraction imaging, XRDI, is a technique to detect crystalline defects in wafer substrates. Small angle X-ray scattering, or XCD, is used to measure the shape or CDs of 3D structures. XRR, X-ray reflectivity, is used for thickness, density and roughness analysis of thin films. And then XRI, X-ray imaging, is used to visualize features such as bumps or through silicon vias. In this presentation, I will focus on micro-XRF and on TXRF. So, Bruker is a partner in the metrology work package in the Meno4 consortium, aiming to develop metrology platforms for enhanced productivity. Bruker is active in two subtasks. The first is focusing on metrology for front-end and back-end characterization. In this subtask, we look at micro-XRF for metal thickness and composition analysis. We work together with X-ray source supplier Excelum, with whom we assess the prototype of their latest liquid MetalJet source. This is a small spot source with a high brilliance. For more details on this source, I'd like to refer to Simona Lasa from Excelum, who also presents in this session. The goal we set ourselves in the beginning of the project is to increase the detected micro-XRF flux on known samples by a factor of 10, while keeping the small spot size. The second subtask is focusing on metrology for contamination control. Here we look at TXRF for metal contamination monitoring. The goal was to increase the sensitivity for light element detection by a factor of 10 and to enhance the throughput by a factor of 2, compared to the TXRF tool that was available in the beginning of the project. In the following slide, I'll explain you briefly the principle of XRF, and I'll give you examples of how micro-XRF is used in the semiconductor industry. This is a brief refresher on what is X-ray fluorescence. So we hit the sample by a primary X-ray beam. And by doing this, it's possible that electrons from the inner shells are knocked out, and this will leave a hole in the electron shell, which then immediately filled by an electron from a higher shell. And this jump creates a photon with a specific energy. Filling this void with an electron from the L shell generates a K alpha photon, and when the electron came from the M shell, it is a K beta photon. We can measure these photons with an XRF detector. Each element has a unique series of fluorescence lines, which allows for qualitative analysis of the sample. The measured intensity is proportional to the number of atoms in the irradiated sample volume. So if we have a reference with a known quantity of the element, we can calibrate the system and perform quantitative analysis. We can measure the thickness of metal films and stacks, or measure the concentration in alloys. It's a beautiful technique because it is non-destructive and requires, which is especially the case for semiconductor wafers, no sample preparation. So micro-XRF is a technique that perfectly lends itself for inline process monitoring. On the right-hand side, you see the typical flow of how micro-XRF is used in the fab on production wafers. The wafers are routinely measured on specified measurement pads or devices. The Bruker tool converts the obtained spectra, you see here, into meaningful data for the customer, for example, the thickness of a specific film. This parameter is then sent to the fab host, where it will be tracked to ensure that the production is within the required process specs. Some technical details on the state-of-the-art XRF channels at Bruker. So on the source side, we have a choice between various anode materials. Which one is selected depends on the applications of the customer. The typical anode materials are molybdenum, copper, rhodium, and tungsten. Through capillary optics, we can create a small spot beam with typical widths in the range of 15 to 35 micrometer. The beam comes from 90 degrees above the sample, and therefore the setup has a low sensitivity for errors in sample height. The small spot allows for measurements basically till the wafer edge, so the edge exclusion is very small. On the detector side, we work with STD, silicon drift detectors, for efficient photon collection that does not require cooling with liquid nitrogen. We can mount up to 4 detectors in the tool to increase the detected flux. The system comes with an automated pattern recognition for accurate positioning, and the benefits of this technique are obvious. XRF is a fast technique, and as I mentioned before, it is non-destructive, so it can directly be applied on product wafers. This is one example of an XRF application used in memory. XRF is used to control the tungsten recess in 3D NAND structures. On the right-hand side, you see the typical 3D NAND stack with alternating oxide-tungsten pairs. Changes in tungsten recess only make up for about 1% in sample volume, therefore a high sensitivity is required. We could prove that our tool has a 3 sigma relative standard deviation of less than 0.15%. So we are sensitive to the changes in the DOE, but also to variations across the wafer. Another example shown here. Electroless plating stacks are used in power chips, especially for automotive. These metal pads are a few hundreds of nanometers of palladium on a few thousands nanometers of nickel on thick copper. And sometimes this is then topped by a thin layer of gold. It's important to monitor the thickness of each film in the stack. With micro XRF you can do that in tens of seconds, in line and on product wafers. The last example comes from wafer level packaging. As you may know, lead-free solder bumps are now commonly used. And these consist of an alloy of tin and a little bit of silver, typically a few percent. The silver content has an influence on the bump reflow temperature, and therefore it is important to monitor it routinely. Also, under-bump metal thickness must be monitored. So this can all be done with micro XRF. One of its key advantages is that it can measure single bumps. Now, wafer level packaging has a pretty aggressive roadmap for the bump size and pitch. So that also imposes new requirements on our XRF channel in the near future to shrink the spot size so that it can keep up with the industry's requirements. In this couple of slides, I'll give you a brief introduction to the technique and application of TXRF, which is a technique to measure metal traces on the wafer surface. The principle of TXRF is very similar to XRF. We hit the sample with an X-ray beam and we measure the fluorescent photons with an STD detector. Now there are two big differences. First, with TXRF we use a monochromatic beam. In micro XRF it is a polychromatic excitation. Show it here. The second big difference between the two is the incident angle of the X-ray beam with respect to the sample surface. In micro XRF we hit the sample at a high angle, like 90 degrees, and in TXRF we hit the sample surface at an angle that is below the critical angle of the substrate material. So therefore the X-rays do not penetrate into the substrate but are reflected on the surface. This then creates the so-called X-ray standing wave field, which is the constructive interaction between the incident monochromatic beam and a totally reflected beam. And this setup is then used to measure traces of metals on the wafer surface. So you can say that by the standing wave, the contaminant is excited twice, once by the incident and once by the reflected beam, and therefore amplifying the fluorescent signal. To be able to detect the smallest traces, it is important that the background in the measurements is as low as possible. So this is firstly achieved by the monochromatic excitation, and by the fact that the X-rays do not penetrate into the substrate. And also typically we work on a vacuum. And altogether this leads to excellent detection limits down to E9 atoms per square centimeter. And also for XRF it is a non-destructive technique and it does not require any sample preparation with chemicals. The driver for chips manufacturers to monitor metal traces is yield optimization. It is needless to say that optimized yield saves costs and gives a competitive advantage. There was an example of a manufacturer who saved millions in only half a year by improving yields through better monitoring. Contamination control is one aspect of yield control, and within this field, metal contamination control is vital. This is because metals of all sorts, from sodium to lead, can degrade the device performance in many ways. And metals can be introduced at every process step, through the equipment, the materials used, or by humans who work in the fab. Now I'm going to show you the progress we've made in micro-XRF and TXRF in the Main4 project. So in subtask 3.1.2, we work together with Xcelem to push the micro-XRF performance. We are running tests on a prototype of the latest generation liquid MetalJet source. The source has a gallium liquid anode. You can see a picture on the right hand side. Xcelem has set up a test bench with the source. Bruker provided the X-ray optic and a state-of-the-art silicon drift detector. So we used this setup to run benchmark tests against the known state-of-the-art solid-state microfocus tubes. Here you see a picture of the gallium source on the left. In the center you see the bench setup at Xcelem. Daniel Larsen from Xcelem and Alex Stoker, my colleague at Bruker, are in this photo. And as you can see, the visit took place right before the COVID pandemic hit us. Two sample types were measured that are relevant to semiconductor processes, namely thin titanium nitride and thick tungsten. First results showed a 5 to 10 times improvement in detected flux compared to the common solid anode microfocus tubes. Such boosted flux will increase the throughput of the micro-XRF measurements in the process and are eventually beneficial to the end customer who experiences an enhanced productivity. This table summarizes our initial findings. The liquid MetalJet source shows a great improvement in fluorescence intensity compared to the common solid-state microfocus tubes on the same samples. Also, the spot size fits the requirements. The concept of the liquid anode is that the power load can be much higher compared to a solid-state anode. And this is beneficial because flux scales with the source power. Our tests have shown that the extra optic may need some modification for best results because these optics, as they are optimized for the common microfocus tubes. On the beam path for the MetalJet is horizontal, whereas the common solid-state microfocus tubes will have the full degrees of freedom to mount the source. For the next subtask, we work on improvement in the TXRF tool. We said in our proposal that we wanted to improve the sensitivity for light elements, sodium, magnesium, aluminum. In the Meter4 project, we have adapted the light element excitation and detection. We also wanted to improve the throughput for full wafer mapping. To reach this goal, we implemented a laser-based align meter to speed up the time to align the wafer to the correct height and angle. The TXRF tool has 3 channels, each optimized for a group of elements. We have a channel for the measurement of transition elements marked with a red box in the periodic table on the right-hand side. The heavy element channel measures the heavy elements marked in blue. The improved light element channel has a high sensitivity for the light elements, aluminum, magnesium and sodium. And we even could see fluorine in certain samples. In the table below, you see the lower limit of detection for the reference elements. The detection limit for aluminum used to be around low E12 atoms per square centimeter, which is now improved to 1E11 atoms per square centimeter and lower, so more than a factor of 10. The beauty of TXRF is that it is a non-destructive method and it is possible to measure full wafer maps that show you where on the wafer the contamination is located. I put an example of a map of sodium on the right hand. As you can see, the tool is sensitive to the very wafer edge. A full wafer map on a 200mm wafer with wafer alignments on every side used to take almost 1 hour to measure in the beginning of this project. Now we can measure this about 2 times faster, still aligning the wafer at every site. So these are altogether very nice productivity improvements obtained in Made in 4. This brings me to the end of my talk, where I'd like to look ahead on what's coming after Made in 4. Regarding micro XRF, this technique is already present in HVM. However, the requirements on spot size and precision are only getting tighter in the years to come, so we must continue to push the performance of our micro XRF tools. In addition, a more powerful macro XRF tool would also open the door for more applications, especially in advanced logic and memory. So Bruker will continue the collaboration with XLM for smaller and more brighter X-ray sources to reach that goal. The metal contamination project will shift focus towards the localized detection of hazardous elements and metals on product wafers. And this brings me to the end, and I'd like to thank you for your attention. Goodbye.